Hello, this is Camille Fairborn from Michigan State University, and I'd like to welcome you to today's Cause Teaching and Learning webinar. We're pleased to have as our presenter today Dr. Jeff Witmer, who is a professor at Oberlin College. For today's webinar, he will give a presentation entitled Regression to the Mean / the Regression Effect. The way the webinars work is that all listeners are muted during the webinar. You can ask questions at any time by typing them into the questions box. We'll be sure to ask those questions towards the end and give the presenter a chance to respond. You can also use the chat box if you're having any technical questions, and I'll try to answer those right away. At this point, I'll turn things over to Dr. Witmer. Jeff, go ahead.
Okay, so thank you for joining us, folks, and I'm going to talk about regression effect and regression to the mean. And I have some PowerPoint prepared. I'm going to actually go back to that in a few minutes. I'm going to start with something just using RStudio. So I'm going to skip over the abstract and talk about the graph of averages. So I think you can see my RStudio screen. The word regression actually goes back to Francis Galton 100-some years ago. And the example that I typically use with my stat classes is talk about using father's height to predict son's height. Now, scatterplot shows a little bit over 1,000 data points, one per family, father and one son. And I want to focus on 65-inch tall fathers. And think about how tall is the typical son of a 65-inch tall father. And this blue dot in the middle is the average of y at that value of x. So when dad's 65 inches tall, rounded to the nearest inch, the average son is at about maybe 67 inches. And I can do a similar thing for the entire scatter plot. Slice it like a loaf of bread. And inside each vertical slice, find the average value of son's height. Those are the blue dots there. And I'd like those points, those blue dots, to be collinear. And so I squeeze them down to make them collinear, and I get the regression line. So I think of the regression line as a smoothed out graph of averages. And I want to add in the SD line. The dashed red line is the standard deviation line. Starts at the middle, average father, average son. And then on the SD line, when you go up by one SD, and it's convenient that for fathers and sons' heights, the SDs are basically the same, roughly 2.3 inches. So if you go up by 2 inches on father's height, the SD line goes up by 2 inches on son's height. And out at the right, if dad is really tall, let's say around 74 inches tall, the SD line predicts the son to be also about 74 inches. The regression line makes a prediction much closer to 70 inches. And that drop-off is the regression effect. So now let me go back over to PowerPoint. And look at the PowerPoint slides that show the same thing. Okay, come on. Why does this always take so long? Okay. So my computer's suddenly very slow. So we just did that and that. And so SD line is go up by one SD on X, go up by one SD on Y. Regression line, go up by one SD on X, go up by a fraction of an SD on Y. That fraction is exactly the correlation coefficient. And the difference between those two is the regression effect. So the SD line is the naive line. If I didn't understand what regression was, I would think if dad is really tall, then junior should also be really tall by the same amount. And in fact, if dad is really tall, his son tends to be taller than average, but not by as much as his father. And the drop-off is the regression effect. In this case, the correlation is real close to 0.5. So if dad is 4 inches taller than the average father, his son is about 2 inches taller than the average son. Taller than average, but not by as much. So that's regression. And I tell my students, if Galton himself had been a short man and had looked at shorter families, if dad is 4 inches shorter than average, the SD line predicts son to be 4 inches shorter than average. The regression line says you're actually going to move toward the mean you're going to move up by a couple of inches. And we talk about correlation and progression if we were focusing on the left-hand side of the scatter plot. But Galton was tall. He thought that height was a good thing. He thought if Dad is really tall, it's a pretty good thing for Dad. Junior is not as tall because he and his cohort have regressed toward the mean, and that's where regression comes from, the terminology. Conveniently, the slope of the least squares line is just the correlation coefficient scaled by the ratio of the two standard deviations. And so the slope of the SD line is simply the ratio of the two SDs. The slope of the regression line is less than that. It's that ratio of SDs scaled by the correlation. So the regression line is not as steep as the SD line. There's some algebra. You can read the algebra later. We'll talk about some examples. So father and son's height is the first example that we just did. Another example that I often use with my students is a really simple test-retest example that I got from Maury de Groot's math stat book from, oh gosh, 35 years ago. De Groot came up with the example, and it's artificial, but it makes the point. Two exams. On the first exam, 3 students scored 30, 3 scored 60, 3 scored 90. The average score was 60. The same thing happened on the second exam. 3 30s, 3 60s, 3 90s for an average of 60. So identical averages, identical standard deviations on the 2 exams. In fact, if you look at the 3 students who scored 30 on the first test, they scored 30, 30, and 60 on the second test for an average of 40. The 3 60s on the first exam scored 30, 60, 90 on the second exam for an average of 60. The 3 A students on the first exam who got 90s on the second exam scored 90, 90, and 60 for an average of 80. Correlation works out to be 0.67. Here's a plot of that. I jittered the data so that you can see there in the bottom left corner, 2 students who scored 30 both times, and 1 scored 30 the first time, 60 the second time. In the top right corner, 2 students scored 90 both times. 1 student went from a 90 down to a 60. And the middle students, 3 60s on the first exam, followed by 30, 60, and 90 on the second exam. The regression line is the flatter line. The SD line goes right through the middle. It goes through 30, 30, 60, 60, 90, 90. The SD line predicts whatever your score is on the first test, you're going to score exactly the same on the second test. The regression line says, not so fast. The 3 students who scored 90 on the first test average out to only 80 on the second test. And the 3 students who scored 30 on the first test improve to an average of 40 on the second test. That's regression. Of course, this is completely artificial data where the numbers work out to be quite nice. But the same thing happens with any, take any class you've ever taught that had 2 exams on it. Plot exam 2 against exam 1, you get the same thing. So I'll show my students an example of real data. Of course, I always leave the names off of the students, but exam scores from a previous course I've taught. And they quickly understand, of course, I tell them it would be much easier on me if they were robots and always got exactly the same score. I could just give 1 exam and that would be it. If a student who scored 90 on the first test scored 90 every single time after that, I'd only have to give 1 assessment. But because of day-to-day variability and how people perform, the regression effect happens. And a regression fallacy is if the dean says to me, Jeff, we gave you these 3 students, these really hot students who scored 90 on the first test. On the second test, after being with you for another 5 weeks, they only scored 80. What's wrong with your teaching? And I say, well, what's really great about my teaching is you gave me 3 students who were pretty bad, who only scored 30 on the first test, and they improved to 40 on the second test because I'm a brilliant teacher. Those are 2 regression fallacies. The regression effect happens because of correlation and imperfect performance. And regression fallacy consists of making up an ad hoc explanation for what you're seeing in a regression effect. Another example, getting the drop on blood pressure is, actually, let me pop over to here. This is a Science News way back in 1987. Some folks came up with a whiz-bang treatment for hypertension. That is, rather than giving people medication or changing their diet or some such thing, these doctors said, how about you come back in 6 weeks? We'll monitor your blood pressure for 6 weeks and see what happens. And what happened, of course, was people who were hypertensive, 6 weeks later, their blood pressure was not so bad. They had improved. They were still above average, but not by as much. And the notes you see scribbled on the side, like it says over here, garbage. This is what my advisor wrote when he read this article. He sent me this thing after he marked it up. These folks did not understand the regression effect. And if you take a bunch of people who are hypertensive and monitor them for 6 weeks, their blood pressure is going to improve. Here's a little example that I made up. Again, it's artificial, but I think it gets the idea across to my students. Suppose you have exactly 6 blood pressure patients at time 0, time 1, and time 2. And 3 of them have the blood pressure go up and then return to normal. And 3 have blood pressure go down and then return to normal. So at time 0, time 1, and time 2, the average blood pressure is the same in the population of these 6 patients. You see them at time 1. At time 1, they enter your clinic, and you measure their blood pressure, and 4 of them are above the dashed line there for what's considered normal blood pressure, and you label them as hypertensive. The other 2, the 2 who are below the dashed line, you tell them, go away, you're healthy, we don't need to see you again. But the 4 people above the dashed line with high blood pressure, you tell them, gosh, you got a problem, we could give you drugs, we could put you on an exercise program, we could change your diet. Instead, just come back in 6 weeks. And 6 weeks later, you see, of those 4, 3 blood pressures have gone down and 1's gone up. As a group, these hypertensive people have improved from time period 1 to time period 2. That's simply the regression effect. And these folks who wrote this article that end up in Science News did not understand that. My advisor, Don Berry, says sometimes, the placebo effect is the regression effect. We all teach placebo effect to our students. They all understand it. I mean, for my students, on the first day of the semester, I mentioned the placebo effect, and they already know what it is. They've heard it before. They've seen it before. They can give a pretty good explanation of what the placebo effect is. They don't know what the regression effect is, but one assertion is the placebo effect is the regression effect. You got 2 groups of people. Group A gets the drug. Group B only gets the placebo. And you see that later on, both groups improved. The drug people improved because you gave them a drug and they got better. The placebo people improved because of, and people typically, students say, oh, they improved because of the placebo effect. Well, what if they simply, the thing that you're studying is, how are you feeling? I understand that you have a cold. Gosh, you're sick, you're sneezing, you're sniffling, and so on. You got a sore throat, stuffy nose. Come back in 2 weeks. We'll see how you're doing. And 2 weeks later, wow, they've all improved. Yeah, because colds only last 7 to 10 days. That's an extreme example, but the same thing happens for anything else in medicine. People who are above average on whatever it is you're studying, the pain level is high today, the blood pressure is high today, whatever else it is, as a group are going to tend to drop back toward the mean, even if you do nothing for them. And if you give them a placebo, you might think, oh, the placebo is what did it. Maybe all that happened was simply the regression effect. Okay. I have a bunch of other examples that I'm going to run through kind of quickly. But one I talked about is traveling salesman keeps a log of what town he's in, how much he paid for dinner, because IRS requires that for tax write-off purposes. He also writes down how good the food was. If the food was really good at a restaurant, then the next time he's in that town, he goes back. And what he experiences is the second time he goes back to a restaurant that was really, really good, a great meal the first time, the second time the food is It's good. I mean, it's better than average food, but not quite as wonderful as the first meal was. Well, it's regression effect. There are two ways a meal can be good. It can be that the restaurant is a good restaurant, or it could be the particular meal, that thing you ordered off the menu the first time, happened to be really good that day, just by luck. If he only goes back to places that are really good the first time, the second time he's going to tend to be somewhat disappointed. And I point out to my students, the same thing happens in other areas than just going to restaurants. You have a really great experience in some way, you tell your friends about it, and then the next time you have the similar experience, it's not quite as wonderful as the first time. That's regression effect. If you want to be pleasantly surprised, go back to the really, really bad restaurants, and the second time the food will be bad, but not quite as horrible as it was the first time. George's SAT prep school, a bunch of students who scored 650 on the math part of the SAT wanted to improve their SAT math skills, so they paid George $500 each and went to George's prep school for 2 months and retook the SAT, and they only averaged 650 again the second time. You've been hired by George to help his lawyer defend him in court against the charge that he ripped off these students because they didn't actually get better. Regression effect. Boomerang CEOs, this was in the New Yorker about 2 years ago. Someone's a CEO at a company. They do really, really well. Some do really well. The people who are really great at a company get hired at another company, and the second time they don't do quite as well. Their second company does not have the same wonderful, wonderful performance that the first company had. Well, yeah, there are two ways that you can do well as a CEO. You can actually be a good CEO, or you can be lucky, or some combination. And if you happen to have good luck with the first company, your company gets a patent just at the right time or whatever else, sales go up for your company, not because you're great, but because the timing was lucky for you. Luck does not persist. You see the regression effect happening. And examples from baseball, I'll skip this, the sophomore slump. Sports Illustrated cover jinx. Just this morning at breakfast, I was reading Sports Illustrated, and one of the letter writers wrote in, mentioned the cover that was on Sports Illustrated 2 weeks ago and said, I don't want to invoke the SI cover jinx, but blah, 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 blah. The SI cover jinx is if you as an athlete perform amazingly well, you get on the cover of Sports Illustrated, and then after that you don't do as well again. Yeah, you're amazingly good and lucky combined. That's how you got onto the cover of the magazine, and your amazingly good luck does not persist. And you can read that later. The Dodgers were on pace to set a record for wins in the baseball season this year. They did not keep up the pace. I like Jason Werth example. Joe Posnanski, one of my favorite authors, noticed some years ago when the Washington Nationals gave Jason Werth a huge contract. He pointed out in 2010, and Posnanski is not a statistician, not a mathematician, he's an author. He's a good author. He's not a math guy, not a stats guy, but he understands variability. Jason Werth played 16 games when he was on the Phillies. He played 16 games at the Nationals Stadium, had 16 good games. The Nationals thought, wow, this guy is really good at hitting the baseball in our stadium. Let's give him a boatload of money because he's really good at our stadium. We'll have him play at our stadium all the time. We're making him part of our team. And Posnanski said in 2010, no way Jason Werth is going to keep up that pace in 2011. And he didn't. He dropped off as expected. He dropped off actually quite a bit. He was pretty bad in 2011. But 2010 was a very good year for him. He had one really good year, did not keep up that pace. Regression effect. And husbands and wives have positively correlated IQs. So a really smart wife tends to have a husband with above average intelligence, but not quite as high as the IQ that she has. And the same is true if you reverse the role of husband and wife. But my favorite example about regression effect, the one I always say, so in my classes I tend to do one example per day for several weeks, taking the first 3 or 4 minutes of the class with these examples. The one I save for the end, the best one, is on training to be a pilot. Kahneman and Tversky, back in 1973, pointed out that what happens is a bunch of people training to be pilots, and each day they go through some particular maneuver, and they get graded basically on how well they did. And at first, the instructors would see if someone who did well, they would praise them, say, you know, good job, keep it up, you're doing a really fine job. If someone did badly, they would yell at them for screwing up. And they noticed that if they praised someone on Monday, on Tuesday their performance would drop off somewhat. If they yelled at someone on Monday for screwing up on Monday, on Tuesday they'd be better. They got lots of data like this. They observed over and over again, if people had a really good performance on Monday, they tend to drop off on Tuesday. If they were really bad on Monday, they tend to improve on Tuesday. And they were praising the people who were good and yelling at the people who were bad. And the logical inference that I came up with was praising people leads to a decrease in performance. Yelling at people leads to improvement. Let's yell at everyone all the time. And Kahneman and Tversky, there's a quote here that you can read later. I tell my students, they're not going to be Air Force pilots, let alone flight instructors. But they might become parents and observe the behavior of their sons and daughters, and they won't give them actual letter grades or numerical grades based on their performance, how well they behaved each day, but they will see that if their kid is really good one day and they praise them, the next day the kid will not be quite as angelic. Regression effect. And yeah, I'll skip this also. There's actual data from US Navy flight training that shows the same thing. Last thing I want to talk about is another way to teach the regression effect. Joel Levin wrote an article in TAS back in 1993 in which you do the following. I do this every once in a while, not every semester, but sometimes. I have a black deck of cards, which you remove the sevens, just makes things work better, that I label as truth. And a red deck of cards, random error. I tell the students, you know, take the deck, shuffle, draw a card, write down what you got, put the card back, hand it to the next person. And do that for red and black. Then each person gets a score. Your exam score is red plus black. Then, after everyone in the room has an exam score, I find out which 5 or so students had the lowest exam scores and which 5 or so had the best exam scores. Then I invoke the spirit of R.A. Fisher, and you can be as dramatic in this time as you want. Often I'll dim the lights and so on. I tell R.A. Fisher to come and help the students who screwed up on the first test to improve. Then I distribute the red deck a second time, and everyone gets a second exam score. Truth stays the same, random error changes. Compute the average for the low and the high, and make a plot. Here's the, last time I did this, the correlation was about 0.77 between exam 1 and exam 2. The students in the bottom left had the 4 lowest score. I chose 4 because I wanted to break. I didn't want to get ties there at 10. So I took the 4 lowest scores in red, and they improved from 7.5 on the first test to 9.25 on the second test. That's evidence that R.A. Fisher's spirit can really help students improve. Sadly, though, it seems this improvement came at the cost of people in the blue group who dropped down from 22.25 to only 21 on the second exam. Regression effect, right? The chance error is changing from one exam to the next. Beth Chance sent me a NPR video, audio clip about regression effect. There's the link. Bill Peterson pointed out a Milt Friedman quote. I suspect the regression fallacy is the most common fallacy in the statistical analysis of economic data. And one last example from Carl Morris. If you want to reduce accidents, find the top 10 accident sites in the past year and put yellow ribbons at the light posts at those 10 intersections. The next year, accidents go down. Did the yellow ribbons cause a reduction in accident rate? This was, I think, hypothetical when Morris said this, but something like this was done in London in 2005, where cameras were put in to reduce deaths and serious injuries. And they found, wow, these cameras really work. But much of that improvement was actually just the regression effect. Okay, so again, I went through those slides kind of quickly. You can read the details later if you want. The quotes you can read at your own leisure. But I think I'm going to stop there because I've gone through all the slides. And I want to leave time for some questions.
All right. Yeah. Thanks, Jeff, for your presentation there. If you have questions you'd like to ask, please go ahead and type those into the questions menu, right, or the questions box right now, and I'll ask those to Jeff. Do you have so my question to you, Jeff, is do you have like a bibliography of these examples somewhere that you keep that you would maybe be willing to share with some of us who also teach this topic?
Well, it's what I just put into the PowerPoints.
Okay.
Yeah, the list of, I guess, 14 or 15 examples, those are my favorites.
Okay.
Yeah. But I keep adding to them. The Carl Morris thing about the yellow ribbons, I had not seen that before, and then that led me to the Times of London thing. So these things keep popping up. The New Yorker article about CEOs, that was... what I want. Where's the New Yorker article? Yeah, this one was just back in 2015, the comeback conundrum, where this author did not understand regression effect. And it's just, this is just a regression effect. So these things keep happening over and over again. Keep adding to my list.
Vicky's asking, can we have a copy of the PowerPoint presentation? And yes, Vicky, this will be posted on the cause website under the webinar that Jeff's given today. So if you check back there, the PowerPoints will be there, and also a recording of this session.
Yeah, I intentionally did not give people time to read the quotes that go with some of these articles because I knew the PowerPoint slides would be available to people to look at later.
Right. Well, all right. I think that's, we don't have very many questions today. You gave us a lot to think about and a lot of good resources, so thank you so much for that. And thanks to all of you for attending today. We don't have a webinar planned for next month yet, but we will definitely get that posted as soon as we have it available, and hopefully you'll be able to hear about it through the usual channels. And just as I say that, there's one more question here. So how do you, Paul Zacklin's asking, how do you quantify how much is due to the regression effect? Is there some sort of expected regression in a given instance? You said that most of the change was due to the regression effect, but how do you quantify that with your students?
Yeah, so the drop-off between the SD line and the regression line is, it's the correlation coefficient. So if R is 0.5, as it is for fathers and sons heights, then the drop-off, the regression effect, is 0.5. So it's really, it's based on the correlation. If you don't know ahead of time what the correlation is going to be, like if I give my students 2 exams, I know people who score well on the first test will tend to do well on the second test, but not by as much. Historically, the correlation is around 0.8, I think, for students in my classes. So I can kind of expect a certain amount of drop-off. If you don't know in advance what the correlation is going to be, then you just don't know. But whatever the correlation is, that's the size of the regression effect, essentially.
Okay. All right. So again, thank you. Thanks to Jeff for presenting to us today, and thanks to all of you for attending. And we'll hope to see you at our next webinar. let's see.